Right. Hello, guys. So in this video, we're going to derive the necessary equations for circular motion, and we'll start with defining what angular velocity is, and we're gonna obtain a relationship between angular velocity and linear velocity. Now, if we look at this picture here, so this is a particle that is moving on a circular path. So this circle has a center at O. So we have taken two position A and B. So we're gonna analyze the motion of this particle from A to B. So we can assume that when it travels from A to B, it will make an angle. So this arc length will subtend an angle at the center delta t. So a small change in angle will occur. So we're gonna look at a small change actually. So then it is easy for us to deal with this equation and finally obtain an equation that is easy for us to work with. A simple equation, that is our objective. Okay, so this is the motion from A to B, and first of all, when a particle goes from here to here, you can see that the angle will change as well. There's a rotation. This rotation corresponds to an angular velocity. That means how at what rate this angle is changing. The rate of change of this angle is defined as the angular velocity. So we should denote it by omega, angular velocity omega, and that is d theta by dt, d theta by dt. Now often we denote it as theta dot. This is the angular velocity. Now when you travel from A to B, we're gonna look at a general case. We think that the velocity also changes some. Here, the velocity is a vector. So this is the direction of the velocity at that moment. And v is the speed of that velocity. And here, when the particle is at B, you know that this velocity will always be tangential to the path because it is moving in a circular path. And when it is at B, we assume that the velocity has changed by this amount, delta V. So for a uniform case, delta V would be 0, but we are just gonna look at a general case, most general case. Now, when it goes from A to B, you can see that it goes in a circular path. So here's the thing. Now, what is the arc length here? Arc length would be, from trigonometry, you know that if this is R, the radius is R does not change. When it change the position by delta theta amount, so the arc length, let's call it S, is equal to R delta theta. Arc length is R delta theta. Now, so this motion takes place in a delta t time, right? It takes place in a delta t time. So let me write it again. S is equal to R delta theta, and it takes place in a time delta t. Now we can use linear motion because this is a linear, this is called linear velocity, and this is an angular velocity. If you want to combine these two in a certain way, we have to start from somewhere. So we know how to deal with linear motion using the kinematic equation. So we're going to start there. So what happens is that as delta t tends to 0, this corresponds to a delta t tending to 0. So as delta t tends to 0, you can see that B is almost close to A. So we can assume the S here, arc length is almost linear. We can assume the arc length is almost linear, right? So if it is linear, you know that you can use linear motion, equations of linear motion, right? So for arc length is S. Now we're going to use this from A to B, V squared equals u squared plus 2as. You can use this one. We know the arc length. We know the acceleration, right? Linear acceleration. That means a change in velocity within a given time. And this is the final velocity, and this is the initial velocity. So let me rearrange this equation. V squared minus u squared equals 2as, right? So what is the acceleration? That means the linear acceleration, that is 2 v minus u. V minus u. We are still looking at this equation. We are not referring to the diagram state. Delta t, right? Change in the velocity within a given time. And what is s? So from this diagram, you can obtain s. S is r delta theta. So this can be written as v minus u, v plus u, right? This v is not this v, okay? They don't have any relationships. So v minus u can be cancelled here. This can be cancelled, and we are left with v plus u equals 2 r. So I'm gonna put delta t right below delta theta, so delta t. So now v is the final velocity. What is the final velocity? V plus delta v. Initial velocity is v. So this would be v plus delta v plus v, 2r delta theta over delta t. And this would give us the 2v plus delta v. Delta v is a small change in the velocity. Then 2i's r delta theta over delta t. So you know that we can assume this true only when this arc length is linear. So to make that, you're going to have to take delta t tends to 0. That means you have to take the limit of both sides. So if you take the limit as delta t tends to 0 of this 2v plus delta v, and the limit as delta t tends to 0 to r delta theta over delta t. Now you can see that in this case delta v also it will also tend to 0, because as delta t tends to 0, we are dealing with the position B very near to A. That means in that case, we can assume that the delta V also tends to 0. So as delta T tends to 0, we can assume delta V also tends to 0. Then here we are left with 2V, and 2R can be factored out, and delta theta over delta T as delta T tends to 0 is defined as d theta by dt. So 2 cancels out, and we are left with V equals R delta theta over delta T means delta theta dot O. We can call it R omega. So this is the equation we deal with, R omega, a simple equation. V is the linear velocity and omega is the angular velocity. Now these two are related by this constant here, that is equal to the radius. Right. Okay. In the next video, we'll look at the acceleration. Okay, thank you for listening.